In this example, we're going to look at a small system of equations and see what the best fit regression is that's going to pass through the data points that we observed. So in this case, we've made 3 observations. We measured 2 independent variables, one corresponding to each column of A, and 1 dependent variable that is this column vector B. And each row is an observation of the data. So for convenience, if I call the first column of A the X variable and the second column Y, and then B I can call my Z, my 2 independent variables are X and Y, and my dependent is Z. So I want to find what's the best equation where I can take my X and my Y and find my Z and have everything be linear. So first I'll fill in my matrix information that I have. And I'll put that aside for right now. But I want to visualize what's happening here. So I'm going to plot my X values, which were 2, 0, 2, the first column of A, 0, 1, 2, which are my Y values, and then the observed Z values 1, 3, and 10. And I'll use plot 3 for this. Alright, so these are, again, just 3 observations I made with my X, my Y, and my Z values as I have here. So what I'm going to try to be doing is, with regression, I want to find, in this case, the plane that best passes through all of my data points. Now in this case, I only have 3 data points, so I will be able to find a plane that perfectly passes through all of them. But in the next example, it's going to be trickier, where we have a lot more observations, and then we have to really, it's going to find the plane that best passes through our entire data cloud that we have. Right, so the first thing I can look at is I can just take my A matrix as it is, and my B, and I'm going to call this X. I can find the values for X and for B. So in this case, it's saying that 0.75 is the first value of X, and 4 is the second value of X. So what this is telling me is that the plane that best passes through these 3 points is going to be determined by 0.75x plus 4 times y equals z. And that plane best fits my data. But I can actually do a different fit. I can use not just a coefficient times x and a coefficient times y, but I can also add a constant term to it as well. So for that, I don't want just x, or not just my A matrix, but what I'm going to do is add a constant value of 1 to that third column. So what this is going to allow me to do is, when I run my regression with now A with this extra column of all 1s in it, now when I do the regression, I'm going to have some coefficient times x plus some coefficient times y plus some constant term is equal to z. Now you'll see the difference that we come up with here when I solve for the x with this larger A matrix, where I added that column of 1s. I see here that I get 3 values out of it for this second x. So what this is telling me is that the plane that best passes through all of my data points is going to be 2.5x plus 4.5y minus 4 equals z. Now I see the difference between these 2 techniques, where I use a constant term and where I don't. So I'll go back to the first method where I found this value of x. So if I do A times x, that was my estimate to the values of B. And we see that with the first x, where I just use the coefficients 0.75 and 4, that A times x gives me 1.5, 4, and 9.5. But if remember, looking at B, our B observations were 1, 3, and 10. What we can come up with here is something called the residual, which is the difference between our estimate, which is the A times x from that best fit, that backslash operator, and B. So what this is just the difference between my estimates and what was actually observed. So what we see here is that for the first value, I'm 0.5 off. For the second value, I'm 1 off. And for the third value, I'm below by 0.5. However, if I do that same thing for the second method I have for estimating, where I redefine A and add that column of 1s, I see here that my residual is 0, that this plane the 2.5x plus 4.5y minus 4 equals z perfectly passes through all three of my points. Now this is only the case because I have 3 points. As soon as I have one point that is not on that plane directly, then I'm going to have something in my residual. But what's happening here is when I'm using this backslash operator, what's happening is that this residual is being minimized. It's finding the plane that minimizes the total residual. So the difference between my estimates of the points and the points that I actually observed in B. So there's an infinite number of planes I could have used because an infinite number of coefficients I could have put in front of x and y and that constant term. But this specific one with 2.5, 4.5, and negative 4 as those coefficients is one that best passes through, in this case, those 3 points. So based on this regression, I can also now make estimates of places that I did not take a measurement. So for example, if I had a value of x that was equal to 1.5 and a value of y that was 0.5, and I'm adding that constant term, I can now multiply this by that x that I found, those coefficients there, and that's going to give me an estimate as to what the value of b would be, or z would be, under this system. So x is 1.5, y is 0.5. This estimates that my value of z that I should observe is 2. Even though, again, from the original data set, I don't have 1.5 and 0.5. If I make a second estimate, let's just make that 1.5 for x, 1.5 for y. This estimates that my value of z would be 6.5, according to my regression.